when you were playing around with these terms and you're looking what these tail things look like, what, I don't know, what made you think, hey, maybe I'll normalize by dividing by, say, the like ln or whatever?
Okay, so
how did you go with things like that?
So I saw the results. I was looking through the first results. The characteristic I was able to find in the previous results from Otsuka, Nakamura, and Professor Liu and Xiao. And now you see here that, okay, we have ln here, that ln, it becomes 1 over ln, and also we go from 3 to 1. And I saw that, okay, it pretty much just jumps by 2s in a sense. So I said, okay, and then the first case when s equals 1, we start off ln, and then second case we start off L2n and also L3n. So I said, okay, this is case 3, so maybe I'll try the same thing and try dividing by L3n. Of course, it took a bit of experimentation at first. I didn't just go, boom, this is L3n. I divided by ln minus 1, ln minus 2, L2n, and I was able to find, hold on, if I was to follow this example, 4 with 4, 3 to 3, 2 to 2, maybe I can find the expression. And that fortunately ended up working for me. And by experimenting with those numbers, I was able to find the coefficient and sort of play around with the ratio. If I divided that by this, if I get like 2 or 4 again, I try multiplying that by that. And I found that if I can play around with that, I'll be able to find this expression. And I followed the same pattern. And also because it jumps from L3n to ln and L4n to L2n, that's how I actually divided the second one by ln instead of L3n again. And that's how I pretty much approached the problem.
How do these big O's distribute themselves?
Oh, so
in other words, you got 1 square out of 4, and the others are linear. Or do you get cubes too, and 4th powers?
No, like
what shows up? What shows up that you've seen?
So I found that it wasn't. I didn't really clearly see this as a pattern, but as I just ended up dividing with Maple, whenever I saw that it was plus or minus and plus or minus, I said, okay, so there must be an error term here that has to be. What do I do to just get rid of this plus and minus sign? Like when I tried to first solve this without the actual O, I was able to find that it was 0.000001 and then negative 0.99999. I said, okay, I still don't want a negative, positive, all the way till the end. I have to get rid of this somehow and have it approached in a positive way. And so I was able to find this. And also this idea also came from the previous results as well.
Well, how far did you go with that, with the powers?
Oh, I went up to case 7.
7? Well, what are 5 and 6 and 7? O of big O of what? There you go.
This would be the expression here.
Oh, it's still no cube. Still no O of 1 over ln cubed, right?
One thing I noticed was that when I did this with the Lucas numbers, it happened to be a lot simpler than what they tried to do with the Fibonacci numbers. Because I've also read articles, not from from Otsuka and Nakamura, but previous researchers, they only considered the floor function. And they were able to find expressions, but even with the floor function, I found the results to be rather complicated. But okay, like I understood that it might be complicated, and I took the challenge and found the Lucas numbers. And I just happened to find that it was a lot more simpler than the Fibonacci numbers. And I saw that, okay, if we go in this fashion, although it's going to get more complicated as you see, it's still going to be the method that's going to work as long as we're able to find the complicated constants like 0.706, etc. If we're able to find those, we'll be able to find the same method of approaching for all s's positive integers.
What if you start with other integers rather than Luca and Fibonacci? Can you still do the same thing? If you start off with the first 2 integers?
Different initial conditions.
What?
From my conclusion, I concluded yes, because as long as it had this, what I concluded was that as long as it had a similar recurrence relationship, I'd be able to use the same method. Also, that was for Fibonacci and Lucas numbers. Perhaps also we've seen for the hyper-Fibonacci numbers. That's how I really started in the first place, assuming that because there are variations that work, I'll find another variation of the Lucas numbers. And by seeing that it also did work, I said, okay, it probably will work for the other ones. That's why in the end I generally want to try to find for the general an plus 2 equals an plus 1 plus an to show that indeed what matters is the recurrence relationship that allows me to go with the same approach.
So if you had a different recurrence, would a similar approach work, or do you really have no idea?
Really, as of now, I say that a similar approach works, which I want to find out later. But I say the only difference really is that the characteristic is the same, but as you see in Fibonacci numbers, if you start 0 then 1, then 2 then 1, they may start off with the same characteristic, but the numbers themselves would obviously end up being different and different and different.
But it's the same recurrence.
Right.
So what if it was like
an
is equal to 2an minus 1 plus an minus 2 or something?
Yeah, right.
That's what I wanted to find in terms of an plus 2 equals an plus 1 and an. But as of now, because that was my assumption that I based off of, which actually ended up fortunately succeeding for me, that the variation would work. That's what I hopefully want to find. I probably want to start off studying more of the sequences, not other than Lucas numbers, and see other variations as well, but eventually get to a general solution for that recurrence relationship and find that what really matters is the recurrence, not the numbers.
So at which stages of your project was Maple used?
Okay, so Maple actually was used towards really the middle of my project, I should say. Well, half the project I really went, like half the project I was really struggling through the identities and trying to find the identities of what worked. And eventually I was able to find that that's when my teacher actually called me. He saw pages of my identities and he said, you don't have to be doing this, you know, and I was able to find that.
So those were like the identity, like L2N equals such and such?
Those results were actually done by hand at that time.
Okay. And then were there other places in which you used Maple? Like it seemed like you used it at least to conjecture what the coefficients were.
I used it to actually find the actual expressions because I wanted to see the patterns of the numbers. And eventually for other cases, I used it for the identities as well. And by using like the previous identities, I was able to find define them as like side relations and find the next relations easier and easier. And I found that just with a click of a computer enter, I'll be able to find the next few identities, and it became more convenient that way. And also for the idea of proof, 1 over xn minus 1 over xn plus xk plus 1, I obviously didn't want to do that by hand as well. So for the actual idea of proof, I actually used Maple as well. I defined one xk and yk on the computer and subtracted and found the numbers that was very slightly close to 0.
Okay, this is probably a silly question, but when I think about zeta functions, I think about the Riemann hypothesis where zeros are. So
that was actually a lot of people's questions.
So for these zeta functions, has anyone studied where the zeros are?
Not really. The main reason why I really wanted to do a zeta function, to be frankly honest, I've just thought that, okay, this is a cool way to name my project in a sense. In a sense that I thought, okay, after studying slight basics of the zeta function, I said, okay, it looks like the zeta function, doesn't look like something's wrong with me here. And I said, okay, maybe we can say it's zeta function like. And I was careful about it. When I first wrote zeta function, my teacher said, no, this is not a zeta function. And this is sort of different. I said, okay, right. So I'll name it zeta function like because it looks like it, just for the appearance of it. And but the main project really was the Lucas numbers and their characteristics.
So, a simplification of that question is, like, can you even talk about things where you go less than 1 for the probability?
Yeah.
We go to 0. So can you talk about extending it to other values where it might diverge consistently?
Not quite. The other results, like for example, like one of the questions that I was asked before, like my New Jersey science fair as well, was what if the numbers became negative and negative? Of course, it would, instead of converging, it would end up diverging. So okay, like those were pretty much the questions. But really, what I really had to clarify was that the project really focused on the Lucas numbers and their sums really, and basing off on previous results of how I can actually get tighter estimates and find better accuracy in terms of how they actually approach the problem.
Thanks again. And so please let me know.